Can you see it?
Yes, I can see it.
Okay. Okay, let me just. Okay, so the colloquium is about the observability of the Unruh effect. Okay, so there is some discussion around about what would be the observability of the Unruh effect, and I would like to see where it boils down. The overview of the colloquium. This is a kind of general colloquium, so I'm not going to be. I am going to be not really technical unless in the first two transparencies. So the overview is the. I will review the Unruh effect very briefly in the first two transparencies. Then I will talk about experimental proposals, and then I go to the conclusions. Look, I prepared this colloquium to be quite relaxed, so you can interrupt me anytime if you have questions. Don't wait to the end if you want. So feel relaxed to stop me and make questions, okay? Okay, so the Unruh effect. So the first two transparencies are the only two technical ones, okay? Okay, the Unruh effect is a effect published by Unruh effect in 1976, and just for historical reasons, I say that the preprint came out in the early summer 1 year before. And we can see this work as the conclusion of a research began by Stephen Fulling in his PhD thesis, where when he published his classical paper on non-uniqueness, canonical field quantization in Riemann spacetime in 73. And basically the main message is that different, okay, let me see, too much technology to me, is that different observers may extract different particle contents from the same quantum field theory. And the Unruh effect is a very good explanation or illustration of this, because we can write two Fock spaces of a quantum field theory in equivalent Fock spaces of the same quantum field theory in Minkowski spacetime. One is the usual one at the left-hand side here in my screen, where we build the Fock space in terms of one particle space of positive frequency solutions as defined by inertial observers. So there is a congruence. There are an infinite number of congruences, but let me take one congruence of inertial observers covering the whole Rindler spacetime. These observers, they know because they follow a time-like killing field. So they know what are positive and negative frequencies. They build one particle space based on this congruence, okay? And then they end up with the Fock space. So this is basic free quantum field theory in flat space-time, chapter 1 of any textbook. The fact is that we can make an equivalent, a distinct construction of the Fock space of the same quantum field theory, where we build this Fock space of the whole space-time associated with the whole space-time as a direct product of the Fock space built by uniformly accelerated observers at the right-hand side, which I call FH1, direct product with FH2, which the Fock space associated with the left-hand side, the Rindler wedge at the left-hand side. Okay, then the message here, in order to make it not very technical, is that precisely the same technique or the same approach that we use to construct the Fock spacetime in the whole Minkowski spacetime is taken by these uniform accelerated observers to construct the Fock space associated with the right-hand side and the left-hand side. And the Fock space in the whole space-time, associated to the whole space-time, is this direct product, which is here. One important thing that I shall comment is that what uniform accelerated observers call a positive frequency state is different from what inertial observers call as a positive frequency particle. Okay, so particles, in other words, making it simple, what inertial observers say to be a particle is different from what uniform accelerated observers define to be a particle. Okay. Then we can take the usual procedure in quantum mechanics and trace out degrees of freedom, say at the the degrees of freedom in the left Rindler wedge. And why? Because if you are at the right Rindler wedge, you are causally disconnected from the left Rindler wedge, causally disconnected. And why? Because you see, if you are in the left, let me go back. If you are in this left-hand side, you cannot receive information. Sorry, if you are in the right-hand side, if you are in the right Rindler wedge, you cannot nor receive information from the left Rindler wedge, nor send information to the left Rindler wedge. So these two Rindler wedges are causally disconnected. One thing I forgot to say before is that the fact that what inertial observers call particle is different from what uniform accelerated observers call as particle is codified in this formula, where we can write the vacuum as defined by inertial observers. When you see this label M, is because I'm referring to inertial observers, M of Minkowski. So the Minkowski vacuum, this state, which is the no particle state as defined by inertial observers, corresponds to this messy thing where these are any particle n particle state with respect to observers as defined by observers in the right Rindler wedge and in the left Rindler wedge. Okay, so the vacuum of the Minkowski space, the vacuum as defined by inertial observers is different from the vacuum of the uniform accelerated observers. Then, if we trace out degrees of freedom, say, of the left Rindler wedge, because if you are in the right Rindler wedge, you are disconnected from this, you don't have access to these degrees of freedom, you end up with a mixed state. But this is not any mixed state, and this is the important thing, because we know when we trace out degrees of freedom, in general, we end up with mixed states, but this is a KMS, a thermal bath. Okay, so this is why, after all, uniformly accelerated observers in the Minkowski vacuum, in the vacuum as defined by inertial observers, corresponds to a thermal bath with respect to uniform accelerated observers. Another thing that I forgot to say is that uniform accelerated observers are described by hyperbolas in the Rindler wedge. Okay, so when I show this, a hyperbola is the word line of a uniform accelerated observer. Okay, and you have a congruence of uniform accelerated observers covering the whole wedge, as we have inertial observers covering the whole Minkowski space-time. Okay. So this boils down in the Unruh effect, and in a nutshell, it says that accelerated observers in the inertial vacuum burn right? At the Unruh temperature, which is proportional to the proper acceleration of the observer, while inertial observers in the same state, in the same Minkowski space-time, they freeze to 0 Kelvin. So you have a inertial observer here freezing to 0 Kelvin, while this uniformly accelerated observer, depending on this proper acceleration, this guy can burn at this temperature, at the Unruh temperature, okay? And you see that the only quantity that is connected to the observer is the proper acceleration. The other things are constants, universal constants. Okay, so in order to make it less strange, although I don't have math to justify what I'm going to say, I like to think of it as reflecting the fact that uniformly accelerated observers, they see as real those particles that inertial observers claim to be virtual. Okay, you are in the inertial vacuum, you only have virtual particles, but these uniform accelerated observers, they see these these virtual particles as being real, and they are as real that they are able to burn the observer if he is accelerated enough. And this is true, contrary to some claims in the literature. Even if this observer is not point-like, it's extended, as shown in this beautiful paper by Van Zel and collaborators in some years ago. Okay, so because there is some confusion about what the Unruh effect is and is not, let me begin emphasizing what the Unruh effect is not. Okay? Okay, let me take one example to illustrate it. Let's assume that I have a detector and a two-part, well, I think information physicists, they call this a two-particle state. This is the same thing, okay? This is my detector. And it begins de-excited, but it's uniform accelerated, okay? So because it's uniform accelerated, some observer is making work on it. And using plain quantum field theory, we can calculate what's the probability of this detector, minimally coupled, say, to a scalar field, to emit a particle and excite. This is thanks to the external agent that makes work on the system. Of course, we can think the same system from the point of view. This is the description. This first description that I just gave you is based on inertial observers, but we can also make the description with respect to co-accelerated observers which are co-accelerated with this uniformly accelerated two-level system. And this is shown here. This is important. This figure at the right-hand side is only important to understand my convention, my graph convention. So you see, because this is not white, is because I'm assuming some thermal state. This is a kind of rose, a thermal state, and this uniform accelerated observer here in Rindler coordinates. In Rindler coordinates, this two-level system is following a word line with psi equal constant, and this is why I have here a straight line, because I have psi equal constant. So this word line is the same of this word line, but described with different coordinates. And tau here is the proper time of the uniformly accelerated two-level system, in contrast to t here at the left-hand side, which is the proper time of the inertial observers. Okay, so these two graphs describe the same situations from different point of views. But the important thing is that the phenomenon is the same. So if I wonder what's the excitation rate with emission of a particle, the answer must be unique, and the answer is unique. For example, making the calculation using your favorite quantum field theory textbook in inertial coordinates, you end up that the excitation rate is given by this formula. Seems complicated, but it's not. Let me just explain. This C naught is the coupling constant between the detector and our particle. Delta E is the energy gap. M is the mass of the field, of the scalar field that the detector is coupled to. And the rest is just, the Bessel function and so on and so forth. So you make the calculation and get the result. That the result is a number of excitations per time. Okay, so this is a plain calculation. But some people think that because of the Unruh effect, this would imply that if I had this two-level system, inertial in a thermal bath, inertial, you see here now inertial, T and Z, these are inertial coordinates. So the fact that this is a straight line in inertial coordinates describe that this two-level system is inertial. And because it is not white, but this is light blue, I mean that this is in a inertial thermal bath. And some people think that the Unruh effect would imply that if I take the same two-level system, make it inertial, but add a background thermal bath with the same temperature of the Unruh temperature, the excitation rate would be the same. This is not what the Unruh effect says, and in this particular case, this illustrates very well this, because although the excitation rate for this uniform accelerated two-level system is given here, as I told you, in the right-hand side, if the mass of the scalar field is larger than delta E, than the energy gap, the excitation rate is 0. So 0 is very different from this right-hand side here. This shows that one cannot interpret the Unruh effect as such, as being such a thing. And how it can be, because in this case, you have a KMS state with this temperature. In the right-hand side, you also have a KMS thermal state at the same temperature. How the results can be different? And the answer is different because although in both cases, they are in a thermal state, these thermal states are made of different particles. And this is why the answer can be different. As I say here, the Unruh effect does not say that the Unruh effect is indistinguishable from an inertial bath at the same temperature, because both these baths are made of different particles. So in Minkowski modes, if you quantize it in terms of transverse momentum and energy, this energy has to be larger than the mass, right? There's this constraint. The energy is larger than the mass because you have to add this frequency, h bar frequency, h bar omega corresponds to energy, and energy accounts for the rest mass plus kinetical energy. Because the kinetical energy is positive, the energy is going to be always larger than that. But this is not so in the Rindler modes. With the Rindler modes, you don't have this constraint. And so the energy of the Rindler modes is larger or equal to 0, even when the scalar field is massive. This is connected with a paper I love this paper, although I think not many people saw it, that you can have three massive particles with total energy E smaller than mc squared in curved spacetimes. So in principle, you can have a particle, say close to a black hole, like the electron, and this electron can be put in a state where its energy is smaller than half MeV, which is its proper mass. And why? Because in a curved spacetime, although we don't think of the gravitational field because the gravitational field is just curvature of spacetime, but if you think in a Newtonian way, the total energy, you have to add this m, which is the proper mass, to the potential energy. And if you think of the potential energy as being the Newtonian potential energy, of course, all this calculation was done in general relativity, but just to give you a feeling of what I'm saying, the total energy, you have to add the potential energy, and the potential energy, gravitational potential energy, is negative, which allows it to have an energy smaller than m. Okay, this is what the Unruh effect is not. So now let me say what the Unruh effect, how it should be seen. It should be seen as an inertial effect, as we have in classical mechanics, of quantum field theory. Because these two graphs are describe the same physical situation, but only from different point of views. I mean, this is the point of view of inertial observers, where this two-level system is uniformly accelerated, and this is also the two-level system accelerated, but now seen from the point of view of Unruh, from Rindler observers, which are uniformly accelerated. Because this is the same phenomenon, the observables have to be the same. And indeed, as we saw, the excitation rate is given by the same formula, no matter whether you make the calculation with respect to inertial observers or uniform accelerated observers. Okay? But this is only true because we have this Unruh thermal bath. So the Unruh thermal bath, this temperature, is necessary to keep consistency between the inertial observer calculation and the uniform accelerated observer calculation of the same phenomenon. If you didn't have the Unruh temperature, you would get a wrong result. You would not have the same observables from the same phenomenon as described by different observers. Yeah, Paulo?
I'm trying to understand the things very recently. And in this situation, I'd like to ask, how can the description in the uniformly accelerated observer, how does this description knows that the system is accelerated? Because
acceleration is absolute. Acceleration is this is a confusion that comes when we learn classical mechanics from classical acceleration and inertiality from classical mechanics, where it seems that we have to have a external observer in such a way to say whether or not something is accelerated or not. Let me give you an example. So in general, people say use distant stars and so on and so forth. But let me give you a very concrete example. Suppose you are in an airplane and you close all your windows, right? You don't see anywhere outside. You don't have to see the airport to be sure whether or not your airplane is on the verge of taking off. Why? Because acceleration is concrete. Indeed, if it accelerates fast enough, you break your bones and you know that you are accelerated, right? Without any external reference. So velocity is always relative, but acceleration, you can calculate the proper acceleration because acceleration is a tensor. You can calculate the scalar associated with it. And this is what you feel multiplied by your mass. This is the force that you feel in your bones when you're accelerated. This is different from velocity, where you also can write it as a vector, but when you take the norm of it, you only get c squared, or c if you take the square root. So acceleration, the answer basically is acceleration absolute.
Okay.
Okay.
Thank you.
Okay. Now, as I told you, the description can be different because in this case, the description of this phenomenon of this excitation rate from the point of view of inertial observers is because there is some external agent making work on this system, and this is what makes this acceleration work. Means that you can have excitation and emission of some particle. From the point of view of uniform accelerated observers, the explanation is completely different. Look at this right-hand side. What happens is that the excitation is because of the absorption of a particle from the thermal bath, because although uniform accelerated observers, they know that this system is accelerated because this is absolute, there is no work because work depends on acceleration and some location, some movement. And here is not, there is no movement because we are making at the right-hand side here the description from the point of view of co-accelerated observers. So co-accelerated, so you write on the system. So there is acceleration because you are on the system, and so you know that you are accelerated. But there is no movement, there is no displacement in space, so there is no work. So there's no work, but there is this thermal bath. And this thermal bath allows the system to absorb a particle, and thanks to this particle which is absorbed, the system, the detector, can be excited. The descriptions are different, but completely independent calculations in each frame lead to the same result, which is here downstairs. And this is precisely what we have in mechanics. In mechanics, if you want to recover results that you get with accelerated systems from the point of view of accelerated observers, you have to add something extra. This something extra is this fictitious force or inertial force, which plays a role in mechanics of the Unruh temperature. If you don't add the Unruh temperature to the uniform accelerated observers in quantum field theory, you get wrong results for the same phenomenon. The same happens in mechanics. If you don't add this fictitious force to the uniform accelerated observers to describe the same phenomenon. Here I have a phenomenon that this guy here in the center throws a ball towards the circumference, to the boundary of this cylinder, if you want. So of course, it may point to this direction, but the ball is going to hit the other guy, right? Here, in order to get the same thing that this guy, from the point of view of moving observers, you have to add a fictitious force, which is going to bound the ball, making it to hit this guy here, which corresponds to this guy here. Okay? Okay, Lucas, please go ahead.
I'm just thinking about something that I don't know if you really thought about this, because according to this description, we should have some fluctuations in the entropy, in the thermodynamic entropy of the system.
Here, you mean?
Yes, exactly. We should have some fluctuations in the entropy. Because we have work, we have this thermal bath, and we have excitation that's irreversible. So we should have some fluctuations in entropy. And this makes me think about the fluctuation dissipation theorem, because I mean, the old paper, the first paper by Einstein, it says that basically says that the fluctuation in entropy is proportional to the specific heat of the system. So can we define a specific heat for the Unruh thermal bath?
Well, I don't have a sharp answer to your question, but my answer is I don't see why you would not, because this is a legitimate thermal state, and whatever questions you make to a thermal state for inertial thermostates, for inertial thermostates, you may also make it's meaningful and legitimate to make for the Unruh thermal bath. Okay. Here, what you're saying about fluctuation of the entropy, because you're probably referring because of the absorption of this particle, right?
Exactly,
okay.
exactly.
So the absorption of this particle here corresponds to the emission of this particle. So the fluctuation of the entropy here that takes just one particle from a whole infinite number of particles in the thermal bath corresponds here to the emission of one particle too, but here in the vacuum. So there is a complete correspondence between absorption of particles in thermal bath and emission of particles in the. I am going through this next. Okay. I'm not going to talk about entropy, but I'm going to say about this correspondence, which is crucial to the rest of the seminar.
Okay. And just one last question, since I'm already talking. I understand why we have a mixed state when we refer just to one of the Rindler wedges. Is there any simple physical explanation why the state must be thermal?
No,
mathematically,
I don't have it, and this is the great. For me, this is really a mystery, and a very deep mystery, because when Hawking discovered his Hawking radiation, it was not a surprise that he would find that black holes would emit some particles because of the collapse, after the collapse of the star. Actually, this before Hawking worked out his effect, Leonard Parker, he had written a project on this to NSF, exactly saying that he would calculate this particle emission. The really surprise and what made him famous because of this is because the thermal emission of the black hole is thermal. And remember that the Unruh effect can be seen as it's linked. I'm not going to go through this here, but it's completely linked to Hawking radiation. So my answer is no. I don't see a priori any reason why this should be thermal, but I guess that this is very deep because the fact that Hawking radiation, black holes evaporate in a thermal bath has many implications and very important implications. For example, for the fact that this process is favorable from an entropic point of view. Okay.
Oh.
So this is a very good question.
Okay. Thank you.
Okay. So we trying to make this point that the Unruh effect is a kind of inertial effect in quantum field theory. We wrote this paper, which was Gabriel Cosella's PhD thesis. But look what kind of feedback we had. Stephen Furling said that the hope is that this paper will convince skeptics that the whole thing is coherent. By the whole thing, he says the Unruh effect, says Stephen Furling. But Vladimir Belinsky, a theorist of international network of centers for relativistic astrophysics in Pescara, says the Unruh effect is nonsense. It's based on a mathematical mistake. Now, Burroughs, who is a well-known mathematical physicist, says that the gas does not exist. So he says that the vacuum will appear hot to an accelerated observer, as Unruh says, but because of a kind of friction that arises through the interplay of a quantum uncertainty and acceleration. So the experiment that we talk here might show the desired effect, but it would not reveal the supposed fog of photons in accelerated frame. Finally, O'Connell says just the opposite. He said that the Unruh's fog of photons exists, in contrary to Buchholz, but the experiment should not produce the supposed signal anyway. So you have anything you want, okay? That this paper makes that the whole thing is consistent, that no matter what we say, what Unruh said, this is completely wrong, the Unruh effect is wrong, that part of the Unruh effect is correct, that the Unruh effect, the gas does not exist, but what we say that is going to happen in spite of the Unruh effect, and here that the Unruh fog exists, but what we are saying to happen here is not going to happen. Okay, so after this, well, this is not, this is the last blackboard by Feynman, and one of the three things that one of the three items he says that he want to learn is the acceleration temperature, which was not trivial to him as well. So probably this is the confusion. The confusion is that it seems confusing at first sight, but I hope that I'm explaining in such a way that there is no confusion or no confusion remains. I hope, at least. This is the goal of this seminar, at least. Okay, so after this, we decided, I think it's important to say, what does it mean to observe it? Because I feel that from a psychological point of view, you have to go to the laboratory to see it somehow in order to make skepticism to vanish. Okay, a direct observation is out of question, because in order to reach 1 Kelvin, you have to accelerate something to 10 to 20 meters per square second. So no body can accelerate to this temperature, to this acceleration so much. And so you cannot reach any reasonable temperature to see it. So you have to go to a different strategy that I call here indirect observation. Here is my map road of what would be to see this effect that doesn't have to be seen because this is an inertial effect. But anyway, let me state what's my roadmap. First, calculate some observable in the Rindler wedge with respect to Rindler observers, uniform accelerated observers, assuming the Unruh thermal bath. So take observers, uniform accelerated, and take a phenomenon and ask them to make this calculation and calculate some observable. Of course, because they are uniform accelerated in the vacuum, they have to take into account the Unruh thermal bath. So any observable they are going to obtain will assume the Unruh thermal bath. Then translate this phenomenon or the result in what inertial observers in the lab should see. So translate this phenomenon calculated from Rindler observers with respect to inertial observers, theoretically, and then go to the laboratory to confirm it. If the experiment in the laboratory confirm point 2, because point 2 has to be obtained, first of all, from the point of view of accelerated observers, which use the Unruh thermal bath, then touché. You have the Unruh effect would be experimentally confirmed. Because the rest of the seminar is going to be based on this, if you have any question of this, please raise your hand, because this is very important that you understand. If you want me to repeat it again, I can do it. Yeah, Paul?
So let me see if I understood.
Mm-hmm.
So you calculate some observable for somebody who is also accelerated in the accelerated referential frame, right?
Right.
And then you calculate what somebody would observe in the inertial frame, okay? And try to measure it. Yeah.
Assuming vacuum.
Assuming
right?
vacuum, okay. But
because they are inertial.
yeah, but so what kind of observable could because when you try to measure to make an experiment to observe this Unruh effect, we always think about measuring the emitted photons, right?
I will give you examples.
Thermal light.
I will give you examples of how these three steps can be followed. Okay, I will give you next examples.
Okay.
But again, just to make stronger, I think clearer. Sometimes students are shy. Let me take this mechanical example let me use my strategy to experimentally prove the existence of, say, centrifugal forces, okay, or Coriolis forces, as in this case. Suppose I am in this right-hand side, right, this carousel, and I want to prove the existence of Coriolis forces. So I take this guy in the center of this here, which is who is rotating, and ask him to calculate who is the observer on the boundary that his ball is going to hit when you have some velocity here. And he makes this calculation, and say that this is the guy who is going to be hit by the ball. Okay? Now let us, the point two is, well, he makes this calculation and get the observable. The observable is, this is the observable, not that, not those ones, but this is the observer who is going to get the ball that I'm going to throw. Now we have to, point two is to translate this to the inertial setup. To inertial setup. So here's the inertial setup. The inertial setup assumes that you have a laboratory, the guy is there inside the laboratory, and you have to end up with something, a carousel making this movement, and you have to have something in the center throwing this ball towards the boundary, towards the boundary, and your experiment must confirm that the guy that is going to get this ball is precisely the one that was calculated in the accelerated frame from using the Coriolis force, this fictitious force. If this inertial experiment, right, this experiment in laboratory, hits precisely the observer that was predicted by this guy using inertial forces, then touché. You have proved the existence of fictitious forces, because if you don't use fictitious forces here, you're going to get a different result. You're going to get that the ball is going to hit this guy, that in the inertial case would be to hit this guy. Okay, so I'm just translating this strategy to the accelerated, to quantum field theory. Let me go to example. Okay. The first one is the depolarization of accelerated electrons. And this was proposed by Bell and Linnaeus. And the idea is to use the depolarization of uniform accelerated electrons to prove the existence of the Unruh thermal bath. So Bell is the Bell, our Bell, and he proposed this in '83. Okay? The idea is the following. Take a uniform accelerated two-level system, say an electron if you want, in a uniform accelerated linear accelerator. Here it is, say SLAC, for example, at Stanford, and make the calculation of what would be the depolarization when you ride on the electron. So you have the electron is initially it's polarized, but because it's going in its rest frame, feel this thermal bath. The a calculation from the point of view of uniform accelerated observers is that it's going to absorb, this two-level system is going to absorb a photon, and eventually it's going to depolarize. By depolarization here means excitation. So if the electron is here, it's going to point out in the different direction. So let's go to point 2 and translate this to the inertial frame situation. The inertial frame situation is you are in the lab here outside, right? Sitting here. The electron is accelerated in slack, right? The order line of this, from our point of view, inertial observers, laboratory observers, is a parabola. It's going to emit a photon, but the idea, Bell and A's idea, is to calculate or see at the end how many of these electrons were depolarized. He calculated here, it can be calculated, is depolarized because of the thermal bath. So if eventually you, in the inertial laboratory, see that the number of depolarized electrons is precisely what was calculated in the accelerated frame using the Unruh thermal bath, then voila, you have proved the existence of the Unruh thermal bath. Fine, is it clear? Yeah, Paulo, go ahead.
But the probability that the electron, some electron is depolarized is not as low as the probability of photon emission by a very cold thermal bath.
You mean what's the contribution of the underground thermal bath here to this depolarization?
No, I mean, for instance, if you try to observe the Unruh effect directly by accelerating some two-level system and trying to observe to detect emitted photons, okay? So the probability is very small because it will be very, very cold, 10 to minus 19 Kelvin.
Oh, I see. No, this is
right
because look, not in slack. The point is that in slack the acceleration is not that small. This is why I have a electron in a accelerator, right? Because acceleration is large.
Large.
Large. But there is another problem here. So the acceleration is large. In principle, you could see something, but you don't see anything because of another reason. I don't know if I answered your question. If I didn't, please repeat it.
But then my point is that the probability of observing this observable that you mentioned is as low as observing directly the Unruh effect. And for instance, if you say that you can accelerate strongly the electron, okay?
Yeah.
Why don't you look directly at the emitted radiation?
I'm going to look at the emitted radiation further. I'm beginning with Bell and Linnaeus, but our proposal is precisely to look at photons. Okay, I'm beginning with Bell because Bell is famous. Okay. But I'm going through what you're saying. Okay, so his proposal is to look at the depolarization. Okay, and his proposal is smart in the sense that although we cannot accelerate to 10 to 20 meters per second, his idea is, look, let's use an electron that you can accelerate it really strong, really hard, because electrons are not going to blow up. But there's a problem. Why? What's the problem? The problem is that you not only need a very large temperature in order to depolarize electrons. Electrons have to stay there long enough to thermalize with the thermal bath. And when you calculate what's the thermalization time for this electron to thermalize with the thermal bath in order, to have time enough to depolarize, it stays so little inside the accelerator, inside the linear accelerator between the departure and the final time, that it doesn't have time to thermalize. This is precisely what happens if you pass your finger through a flame. If you make it really fast, no matter how hot is this flame, you're not going to burn your finger. Okay, So this is why, unfortunately, spins have no time to thermalize the Unruh thermal bath, reaching the target in linear before reaching the target in the linear accelerators. In other words, the temperature can be high because the acceleration is high, is large, but because it doesn't have time to thermalize, so this proposal is basically useless. And why is it useless? Why this takes so long to thermalize? Because the energy gap, this energy gap associated with the depolarization is large for for laboratory proposals. So the idea is to make this smaller. But if you make it too small, you don't have any system, but the electron itself. What do I mean? I mean that in order to see the Unruh thermal bath, let's use Unruh radiation, what you say, right? And so let us calculate from the point of view of uniform accelerated observers, not the depolarization of the electrons, but how many photons they scatter because of the Unruh thermal bath. So here we have the electron, the same uniform accelerated electron, but rather than looking at the depolarization of the electron, we look at the scattering of the electrons because of the Unruh thermal bath. Okay, so this is what we have to calculate: the scattering of electrons, of uniform accelerated electrons, from the point of view of uniform accelerated observers because of the Unruh thermal bath. Point two, we have to translate it in the inertial observer phenomenon. The translation is this. It is in the right-hand side. Using Unruh, what happens when an accelerating observer detects a Rindler particle or absorbs and emits particles? Using this paper, this phenomenon can be translated in this situation, the inertial frame. Because of the thermal bath, this situation, a uniform accelerated electron emits correlated pairs of photons. So if you are able to see the emission of correlated pair of photons in the inertial frame in the same rate that is calculated in the accelerated frame, so this absorption emission corresponds to this, so you can calculate this rate of emission in the accelerated frame. If you see this, you are detecting the Unruh thermal bath, because in order to calculate this emission in the accelerated frame, you have to take into account the thermal bath, the Unruh thermal bath. Okay, so this is a signal that we had to calculate. But there is one problem. The first problem is that nobody did yet the calculation in the accelerated frame. This is in my list of things that I want to calculate, the theoretical calculation in the accelerated frame, right? In order to make the calculation, legitimate calculation, the accelerated frame, and ask experimentalists to see what we are predicted theoretically in the accelerated frame. But why didn't do it yet? Although I still think this is interesting. Why didn't I do it yet? Because in order, the answer is going to be such that eventually, I'm sure, or actually I'm using these papers, I'm going to say, after doing this calculated accelerated frame, I'm going to say, look, experimentalists, look at this in your laboratory, and you're going to tell me, Paul is going to tell me, unhappily, this is impossible because I need ultra powerful lasers that still they are not available, right? So in order to see this signal, in other words, in laboratory, you would need ultra powerful lasers that you still don't have. Okay, go ahead.
Let me ask a question.
Yeah, sure, please.
Yes, as consider, if you accelerate the electron, it will produce a synchrotron radiation, right?
Right.
So it will emit a lot
Next transparency.
Okay.
Paulo, I hope I have you in all my seminars. Because the reason, exactly, all my seminars, Because the reason why this result is small, because this is a phenomenon with two vertices. Then in order to make this result observable, let's think of Larmor radiation. This is precisely what we are saying. This is basically what you're saying. Look, this result is small, it's difficult to observe because they have a process with two vertices. Why not look at Larmor radiation? It's easier to observe, right, Paulo? So is it possible to look or to identify the Unruh thermal bath using this simpler phenomenon, right? And the answer is yes. And this is precisely what we did since 92, in 20, and in particular, in 20, in particular, in that paper that raised all that controversy, the controversy that I showed you before on science was based precisely in this paper that uses Larmor to identify the Unruh thermal bath. And let me try to convince you that we can see signals or shadows of the Unruh thermal bath in Plato's cave using Larmor radiation. So what's the phenomenon? The phenomenon is the following. Suppose that rather than having a uniformly accelerated electron, I am uniform accelerated, but rather than holding my electron, this electron is is in circular orbit around me. I can get it with a magnetic field. Okay. And the idea is, let us calculate with this difference. Now the electron has this situation. What's the absorption and emission of Rindler particles in the accelerated frame? Okay, so I have an electron. The electron is uniformly accelerated, but it has a circular acceleration as well on the top of it. And we propose to calculate the absorption and emission of Rindler particles in this from the point of view of uniform accelerated observers using the plain Unruh thermal bath. We can make this calculation. Point 2, we have to translate it in the inertial frame situation. This is the inertial frame situation. Let me make it look. This is the uniformly accelerated electron, but this is not a perfect uniform accelerated electron because it has this on top, this circular movement that in this graph appears only as this. I forgot the name in English. Okay, anyway, right? And because of it, I have a accelerated charge making this word line, funny word line. I can calculate Larmor radiation. And this Larmor radiation, I can predict what's the Larmor radiation of particles emitted because I have this uniformly accelerated frame calculation, assuming this thermal bath, the Unruh thermal bath. So I predict it. And then I go to the experimentalist and say, look, so this is the space-time phenomenon, right? I have a uniform accelerated electron that goes back and forth, but also it makes this movement. And so I have this, it stops and goes back. Okay. And I can calculate what is gamma, right? What is this rate of emission? And I can ask experimentalists to calculate it. Okay, look, please calculate what is the rate of emission of photons from the point of view of inertial observers, and see whether it coincides with my prediction that I did in the uniform accelerated frame calculation using the Unruh thermal bath. If you say okay, the Unruh thermal bath is calculated, is observed. Sorry, is observed, is proven. This is the result. This is the result that we ask experimentalists to observe. And here I have three curves because one curve, the correct curve is this blue curve, because here we use the Unruh temperature. These other curves is when, for example, you don't have the root temperature, and here you have a root temperature 10 times larger. You have different curves. In order, you can put some error bars and disprove results with large temperatures with respect to root temperature. Okay? But then Paulo is going to stop me again and say, look, this is complicated because calculating photon by photon for uniformly accelerated, it's much easier to calculate the power emitted rather than, if you have many photons, coherent photons in a Larmor radiation, it's better to calculate the intensity, as Jackson's tell us, rather than photon per photon. To calculate 1 to 10 photons is one thing, but 1 mole of photons is another thing. You're perfectly correct, Paulo. And so we stop at this point, and before asking or contacting you to look at it, we say, look, after all, we're talking about Larmor radiation. Larmor radiation can be calculated using classical electrodynamics. But here we have a prediction based on the number of photons. How can we translate a classical electrodynamics calculation using, a classical electrodynamics calculation, Maxwell equations, into number of photons emitted? Is it possible? And the answer is yes. The answer is yes, because assuming that you allow me to use one quantum simple ingredient that is energy is h bar omega. In other words, if I use Maxwell equations and this extra ingredient, the only single ingredient that's energy is h bar omega, in order to translate radiation intensity in terms of number of photons, we get precisely the same result of the root temperature. This graph here was obtained using Maxwell equations plus this extra ingredient. Maxwell equations lead precisely to the same result that we obtained using, leads precisely or confirms our prediction that was made in the uniform accelerated frame, using the root thermal bath. So unless you doubt Maxwell equations, the Unruh effect is proven. Actually, when we wrote our paper, the title we sent to the editor was virtual proof of the Unruh effect. By virtual, we meant, look, unless you don't believe the Maxwell equation, the Unruh effect is proven. But the PRO editor told me that, look, observation is a sacred word, cannot be used by theoreticians with this virtual thing, right? So you have to change it, and this is why we changed it for proposal for observing the Unruh effect using classical electrodynamics. It was the best we were able to negotiate with the editor, okay? More recently, in 2019, a team from the Technion, they claimed to see this effect connected with the back reaction, radiation reaction of accelerated charges. Okay. To be sincere, it seems interesting, very interesting, but to be sincere, I'm not. As a theoretician, I cannot go and say, look, this is exactly this, and that's it. Okay. But I recommend experimentalists to look at this paper. So I'm going. I think. Okay, please go ahead, Paulo.
Can I ask a question? So I think I understand your proposal, but I'm thinking about so what's the typical wavelength of this radiation? Because you have a shower of very broadband emission in this process. How can I find the signal inside of all of this thing?
Perfect. Paulo, look, these two papers, I suggest mainly this paper here, because after publishing this paper, which is the main paper that I'm telling you, that is the theoretical paper, we went to the best of our knowledge to what you are saying. So we try to see a window that would be possible to observe this effect where, say, for example, excluding noise from telecommunication, excluding noise from thermal baths, from many noises that we were able to compute. I'm not saying that this is the last word. Actually, we published this in a proceeding in order to Atsushi Higuchi, but I think the answer to your question was addressed to the best of our knowledge in this paper.
Okay, let me ask one more question.
Sure.
It's about this classical correspondence. So it sounds funny for me that you were able to predict some radiation that was spontaneously emitted, because this Unruh effect is like a spontaneous emission. And the spontaneous emission cannot be described classically. Okay. Even though if you know that there's a source, you can calculate the intensity, the classical intensity, but you cannot, from principles, you cannot predict that.
I see. Let me go. Let me explain this. I go to Bell-Linnaeus. This is Bell-Linnaeus proposal. Okay. Let us take Bell-Linnaeus proposal, where, assuming a perfect world, we could, see the Unruh thermal bath by the depolarization of electrons. Okay. Look at the description. Okay, let me go. Sorry. Let me go to my example here. Okay, here. In this case, you see, we have a uniform accelerated detector, two-level system. And from the point of view of accelerated observers, from inertial observers, from the point of view of inertial observers, what happens is that the two-level system excites, and there is an emission of a particle, of a Minkowski particle that's going to see in your detector. Now, this description, according to this paper by Unruh and Wald, 84, they showed this for the first time. The emission of a particle corresponds to the absorption of a particle from the point of view of accelerated observers. So the emission of inertial particle, this spontaneous emission of photons in the inertial frame corresponds to the absorption of Rindler particles, because there are other kind of particles in the accelerated frame. We can go further in this paper and reach what we have used in our paper. Or you also use here, but let me go straight to our paper. That the emission and absorption of the combination of emission and absorption of photons in the accelerated frame, they correspond in the inertial frame only to spontaneous emission of photons. So the spontaneous emission of photons in our laboratory, our typical laboratory, inertial laboratories, correspond in the accelerated frame to the emission and absorption of Rindler particles in the accelerated frame. And this is also connected to this. The only difference is that in their case, in 84, because they were assuming only uniform accelerated situation. The uniform accelerated two-level system only absorbed the emission rate vanishes. But because in our case, we are not only uniform accelerated, we are this discharge is also in circular motion. You have absorption and emission, and both these processes correspond to emission in the inertial frame. So each particle emitted or absorbed in the accelerated frame corresponds to the emission of a usual Minkowski photon in the inertial frame. This is a result, non-trivial result, found by the first time by Unruh and Wald.
So what you have calculated was just the rate of emission using the classical electrodynamics.
What we have calculated in the accelerated frame was using the Unruh thermal bath, the combination of emission and absorption of Rindler particles by the electron. Okay? Then we translated it into emission of usual Minkowski photons in the laboratory. This allowed us to plot this blue curve. Then we said, look, let's forget all this and see what Maxwell equations tell us about the emission of classical radiation from the point of view of inertial observers. Let's go. We forgot all this quantum calculation, used Maxwell equations, and calculated the intensity emitted, the radiation emitted by the same source in the inertial frame. Usual Maxwell equation. Then using this extra ingredient, E equal to h bar omega, we translated our classical electrodynamic calculation into photon emission and compared with our quantum field theory calculation. And this is exactly the same. This is not, it's exactly the same. We can show that it's exactly the same.
I see. Okay.
Thank you.
Thank you.
So,
Professor.
I am, yeah, I know I have to stop. So let me skip, but let me just mention that we can have the Unruh effect in classical field theory, traces of the Unruh effect in classical field theory for those who are interested in classical field, in looking at, for example, trace of the Unruh effect on waves in a canal, okay? Which is much easier to see because rather than having this light velocity, you have the phonon velocity, which is much smaller. This makes the corresponding temperature much larger. Okay, so I like these papers here, if you are interested in. And so from our conclusions that the final conclusion is that the Unruh effect has to be there in order to keep consistency of usual quantum field theory in inertial frame. If the Unruh effect is not there, the Unruh effect, you would not be able to obtain in the accelerated frame the same observables you calculate in the inertial frame for the same phenomenon. So thank you very much. Sorry for being ahead in my time, but I think I answered most of the questions. So if there is some remaining question to be answered, I am here.
Thank you, Professor. There's no need to worry about time. There's actually a question from the YouTube chat. Luciano is asking if this proposed experiment requires only uniformly circular trajectories, since there are diverging claims regarding the Unruh effect for uniform circular motion.
Can you repeat it again? Sorry. Yeah.
If this proposed experiment requires only uniformly circular trajectories.
No. We used it just because it's convenient. But actually, the inspiration for this paper came from an old paper, from this paper here, where we use uniformly accelerated sources, electrons. And why we decided to change the word line from uniform accelerated using 92 to this one, because in the uniformly accelerated case, the absorption and emission of particles, if this trajectory was uniform accelerated, a straight line in psi, because psi would be constant in these coordinates for a uniform accelerated trajectory, the absorption and emission would be the absorption and emission of zero energy Rindler photons. We do exist, although zero energy Minkowski photons are meaningless, because by saying that it's zero energy, it also says that the transverse momentum is zero. This is not the case for Rindler particles, but I think psychologically some people have some barriers to accept zero energy Rindler photons. And so in order to vanish or to not enter into this controversy, we decided to use this trajectory. And even so, as you see, it was not enough to, it was our theoretical virtual observation of zero effect was not enough to put down, to lay down, criticisms to zero effect, to zero thermal bath, to what on, people are still confused, I think. And this is why, from a psychological point of view, I think it would be very good to show it, to show traces of it in laboratory, as many as possible. I remember in 2000, by 2000, when Daniel Vanzella was doing his PhD, at the same time, there were a number of papers only saying that zero effect is wrong, basically is wrong. Nowadays, at least, there are less people saying that this is wrong, but still there are people confused about what the zero effect says. And I think that this confusion is only going to vanish if we go to the laboratory and show evidences with error bars. This is my feeling.
Okay, I actually have one question myself.
Please.
The Euro temperature depends on the acceleration, right? And as you pointed out, is an absolute concept. Does this remain true when you consider the curved space-time? Acceleration is still an absolute concept there?
Sure. For example, if you are static outside, say here, now, let me ask you, are you accelerated or are you inertial?
I'm accelerated.
Very good. So you are accelerated because acceleration is an absolute concept, right? And you can see it, how much accelerated you are, if you put a dynamometer at your chair and you divide by your and you multiply and you divide by your mass, and you have the proper acceleration you are submitted to, and you are in a curved space-time. I don't know if I answered your question, because I think you already knew the answer, but anyway.
No, I just kind of want to confirm that.
Okay.
But the Euro effect for curved space-time is well established, or, I mean, theoretically speaking.
I see. Yes, but let us understand what would be the Euro effect in curved space-time. Okay, I can call I can suppose you have, okay, Hawking radiation assumes the collapse of a star into a black hole. The whole space-time, the space-time is not stationary, is not static. But I can think of a similar situation where with a static space-time, assuming an eternal black hole. And if you have an eternal black hole, you can think in a similar situation, because you have both wedges, and can think of a similar a Unruh effect in curved space-time, but rather than having Minkowski space-time as the background space-time, you have a eternal black hole, and then you have similar results. And so the answer is yes, it's well established. I recommend a physics reports 1992, I think, by Bob Wald and Bernard Kay, a physics report, 1992. Physics reports. Okay, where he says about, I think something like quantum field theory bifurcating killing horizon space-time, something like this. I think Paulo has a question.
Thank you.
Can I? So from your demonstration of the electron Larmor radiation using classical electrodynamics, so it seems to me that the visible, observable signatures of Unruh effects are all around, because we can have many particles accelerated, and in our rest frame, we could detect them if we know, if we knew that they have this correspondence in the accelerated referential frame. Do you understand? It seems that we could have been now we could have been receiving. We could maybe we are now looking at photons that came.
I see what you mean.
Which are analogous. Do you see?
I see. What you mean is, why don't we see directly these the photons of the thermal bath that uniform accelerated observers claim to exist? Why don't we see somehow? Right? Why don't we?
No, I think it's if it seems that looking directly at the photons emitted by these accelerated objects, it's very hard, because we should accelerate it very fast in order to achieve some considerable temperature, right?
Right.
This is one thing. But the other thing that I'm saying is that we can have objects that are accelerated, like these electrons that you mentioned, and they will emit radiation because they are moving electrons radiate, right? But we don't know that this is a signature of the Unruh effect, because we don't usually make this correspondence that you did.
Oh, I see what you mean. You are saying basically that we have already observed the Unruh thermal bath.
We are probably observing in the
right.
sense that we are probably measuring, but we don't know that is an
But we don't know it, right? Because nobody did the calculation in the accelerated frame.
Exactly.
It may be very well. Okay, it may be that there, for example, say using many electrons, a number of electrons rather than one or two, right? So this may be a legitimate, I think, quest. And actually, we thought of it. I think when we tried this proposal, we thought this would be the easiest proposal where the Unruh effect could be identified, these shadows in the Plato scale. But there may be other proposals, like this is basically what Lynch, Cohen, Haddad, and Kaminer in the Technion, they claim to have seen. They claim to have seen the Unruh thermal bath, a signal of the Unruh thermal bath in the radiation reaction, right? So I agree completely with you, right? There may be smarter ways of identifying these signals of the Unruh thermal bath that we have already observed in the laboratory, but we did not do the calculation in the accelerated frame using the Unruh thermal bath. And this is the only reason why somebody didn't claim, look, we have already observed the Unruh thermal bath. I agree 100%. 100%.
Thanks a lot. Thanks a lot for
thank you, Paulo. It was good to see you.
Very nice.
So anyone has any more questions or comments? Well, if not, I wanted to thank you again, Professor, for accepting the invitation to
Thank you all. Thank you all.
this talk. Thank you.
Hope to see you personally.
Yeah, hope that one day too.
Bye-bye.
So,
Obrigado,
goodbye,
Jorge.
everyone.
Obrigado.
Palestra. Muito obrigado.
Obrigado, obrigado. Obrigado a todos.
Tchau, pessoal. Grande abraço. O Jorge, precisamos conversar
Oi.
um pouco mais sobre esse assunto aí.
Eu estou à disposição, viu? Eu posso... eu sou um homem virtual agora, mas virtualmente eu converso, tá bom? É só você querer, tiver qualquer observação e tal, estou todo ouvidos, tá?
Tá bom, então tá bom. Vou te procurar então, para a gente bater um papo.
Por favor, faça isso, porque assim, é um tema que eu estou envolvido há muitos anos. Hoje em dia eu estou assim, spreading my shots, né? Mas é um tema que eu estou envolvido há muitos anos. Então, e assim, eu gostaria até o fim da minha vida, né, de ter alguma coisa minha observada de algum jeito.